I'd like to continue on now and give you two more examples of proofs that can be done, direct proofs, without following our very rigid template for providing a direct proof. So the first is this example. Let's use as an assumption that plus or minus the square root of 2 is an irrational number. This is something we actually will prove later on in the class, but for now, let's use it as an assumption. Plus or minus the square root of 2 is irrational. And from that assumption, let's prove that all real roots of the polynomial x to the fourth minus 4 are irrational. So let's walk through the proof of this together. And the proof will really just be a very formal explanation of our reasoning. First, let's go ahead and find all of the real roots of x to the fourth minus 4 by factoring. So in this first statement, what we're saying is, this is the procedure we're going to do. We're going to factor this polynomial, and we'll find the roots in this way. This is our methodology. So we notice that x to the fourth minus 4 is equal to x squared minus 2 times x squared plus 2. Now the next thing we do is we apply the quadratic formula to the term x squared plus 2, this second factor. And when we do this, we see that x squared plus 2 does not factor any further. That is, these are its roots. Its roots are given by plus or minus the square root of negative 8 over 2, which if you wanted to simplify it into complex numbers is plus or minus the square root of 2i. So those are complex roots, and the way that we found them, our justification for that, is by applying the quadratic formula. So since that's a formula that many people have memorized, but we don't want to assume that anybody knows, we want to say where we got our information from, we're going to justify that line of reasoning by saying what we did. And then, maybe we think that that first sentence is a little bit hard to swallow, so we're going to explain further. We're going to say that is, x squared plus 2 has only complex roots. So the real roots, which are what we're concerned with in the problem, real roots, of this polynomial must be given by the other factor, which is this first factor, x squared minus 2. This is a word of caution that they actually bring up in your book of proof, which is a good piece of advice. You want to be a little bit careful with things, with words like it, that factor, this one, that one. It can sometimes be difficult in a proof to figure out to what you're referring. So for instance here I said, x squared plus 2 has only complex roots, so the real roots are given by the other factor. And instead of stopping there and leaving that as possibly ambiguous, I said the other factor. Which one? This one, x squared minus 2. So I'm trying to bring this extra level of being particularly specific to the problem to make sure that there's just no possibility for confusion. Now again, up here I've just restated the problem that we're working on. So this is where we continue the proof. Now, let's further examine x squared minus 2. And this polynomial can be further factored as x plus the square root of 2 times x minus the square root of 2. And each one of these terms contributes one real root to the polynomial x to the fourth minus 4. So what have we done? We've just factored a little bit further so that we can figure out who's contributing a real root. We then obtain the roots square root of 2 and negative square root of 2 as roots of x squared minus 2, and therefore roots of x to the fourth minus 4. Here, we found that square root of 2 and negative square root of 2 are roots of our polynomial, and square root of 2 and negative square root of 2 are irrational numbers by our assumption. So here, we were assuming that plus or minus the square root of 2 is irrational, and because we're using that now, we're going to say this is by our assumption. We're pointing to why we can make that claim, why these roots are irrational. That's our assumption. So justification. Now, as each root of x to the fourth minus 4 comes from one of its factors, and we have considered all factors individually, the proof is complete. So in summary, what did we do? We took our polynomial and we factored it. And as we were going along, we factored it as far as we possibly could until we got to pieces of factoring that either had complex roots or we got down as far as we could, down here to linear roots. And then we took a look at all of the roots of the polynomial. We had 2 complex roots and 2 real roots. We then examined the real roots, which were square root of 2 and negative square root of 2, and we justified that those were irrational by assumption. And since we had thoroughly considered all cases, all of the different factors of x to the fourth minus 4 and all possible roots, we finished our proof. One very last example of a type of proof that you might do that deviates from our standard template is what's called a constructive proof. Now, constructive proofs can be very difficult to do because you've got to come up with sort of a clever idea on your own, as you'll see in this proof example we're going to do. So constructive proofs are some of the hardest that I could ask of you. In that sense, I probably won't ask for you to do anything over the top, but here's an example of a proof that's something that's probably a little too hard to just require of you on your own, but it's a really cool fact, and so I wanted to use it as an example of a constructive proof and a really interesting fact involving infinite sets that I think takes a lot of people by surprise. So here's something that I'd like to give you as a definition. When we're given two sets, A and B, and we want to somehow compare the sizes of those sets. When things are finite, everything is really easy. It's easy for us to figure out when one number is less than or equal to another number. But in terms of infinity, how would we say that one set is smaller than another set somehow when they have infinite sizes? So the way that mathematicians define this is they say that the set A will be less than or equal to the set B if there exists a function, f, from A to B that's a one-to-one function. Your book sometimes calls that injective. So that's a definition that we're going to provide before we begin a proof. And then what we will prove is that the size of the set of the natural numbers is less than or equal to the size of the set of the integers. That's something that seems fairly obvious to us because the natural numbers are a subset of the integers. But in fact, you can also prove, according to this definition, that the integers are smaller, and they have size less than or equal to the size of the natural numbers. In fact, when you're dealing with infinite sets, it's probably better, instead of saying size, to say cardinality. Cardinality of the integers is less than or equal to the cardinality of the natural numbers. And it's this last fact that some people find really perplexing, but it is in fact true. And so in terms of, sorry, I didn't mean to do that just yet, in terms of the integers and the natural numbers, these are infinite sets that actually have the same size. We think of them as having the same size, even though the natural numbers are a subset of the integers, and a subset in kind of a strict way. It somehow seems as that there's infinitely many more elements in the integers than the natural numbers because we have all of those negative numbers and infinitely many of them to consider. But in fact, these two sets have the same size. So let's see the proof of this. First, we're going to prove that the size of the set of the natural numbers is less than or equal to the size of the set of the integers. So let's prove the intuitive one first. Now to do this, so we're going to say what we're going to prove. First, we're going to prove item number 1 on our list. And the second thing we're going to say is how we're going to do this. So to do this, we will act according to this definition. We'll construct a one-to-one function from the natural numbers to the integers. Now, what map are we going to use? We're going to use the map that makes sense to us, the map that is natural and intuitive from the natural numbers to the integers, which is just send an element to itself. Every natural number you could want in the world is an integer, so this map really does go from natural numbers to integers. So take an element and just, it is itself. That's us introducing what the map is. Now that we've introduced it, what we need to check in order to use this definition is that the map that we've defined is a one-to-one map. So for this, in order to understand this proof, you're going to have to remember what it means for a function to be one-to-one. I've defined this for you before, so you may want to go and look it up. But basically what it means, and I'll restate it later, is that if you have two outputs of the function that are the same, then they must have come from the same input. Okay. So that's what we'll do. Under this map, let's suppose that f of x is equal to f of y, and what we need to show then is that the input values for f of x. The input values for f of y are the same as well. Now, to do this, we just use our map. If f of x is equal to y, then what is f of x? Well, according to this rule, it's x. What is f of y? According to the rule we defined for our map, it's y. And f of x is x, f of y is y. And because we're assuming that f of x is equal to f of y, we have that all of these things are equal. X, which is f of x, is f of y, which is also y. And putting this together, we conclude that x is equal to y, which is what we needed to show that f was a one-to-one function. Next, let's move on and let's show that second bullet point. Let's show that the size of the set of the integers, this is a mistake. What this should say is, next, we will show that the size of the set of the integers is less than or equal to the size of the set of the natural numbers, which is property 2 over here. This is the one that we really want to show. So we have a mistake in the proof. Happens to the best of us. And in order to do this, we will use this definition. We will construct a map from the integers to the natural numbers, and then we'll show that this map is one-to-one. So here's the map that we want to define. Let's start by defining it with a few examples, and then we know that that's never really good enough for a full proof of what we're doing, so we'll formalize after we've looked at a few examples right away. So this is how we want to start out. Let's start by taking 0 and sending it to 1. Then let's take 1 and send it to 2. And then let's zigzag back around to the other side of 0. And let's take -1 and let's send it to 3. Then let's hop back around and send 2 to 4 and -2 to 5. And we would keep cycling around 0 in this way. So we would go and we would send 3 to 6 and -3 to 7 and 4 to 8 and -4 to 9. And so on and so forth. And after looking at these examples are never proof, we need to come up with a way to write every integer as a natural number. And this is the rule. We'll take f of an integer and we'll send it to 2 times that integer. So again, another mistake. Wow, this is really terrible. We'll take an integer n and we'll send it to 2 times that integer if our integer happens to be a positive number. So notice that that's what's happening. The positive integers, 1, 2, 3, etc., go to 2, 4, 6, and so on and so forth. So f of n is 2n if n is greater than 0. And what do we do for the numbers that are less than or equal to 0? Well, we take them and we send them to, because they're negative, we send them to -2 times whatever they are. So this -2 times n is actually a positive number, because remember n is not positive, it's basically negative in this case. And then we add 1 onto that in order to make sure that we have an odd number. Now, notice that this map really does go from the integers to the natural numbers. So we've ensured that every integer, positive, 0, or negative, has a definition according to this function, and we've always mapped starting at 1, and we're always increasing from there. This really is a map from the integers to the natural numbers. And what we need to do to finish this part of the proof is show that the map is one-to-one. So here what we've stated is, we've reminded our reader at this point of what the definition of one-to-one is. We said to see that this map is one-to-one, we have to show that if I start with 2 integers, x and y, and they have the same output via this function, f of x is equal to f of y, then we need to show that x is equal to y. So in this constructive proof, we must now do a very little direct proof where it does make sense to follow our template. We need to assume that x and y are integers and that f of x is equal to y. And then what we need to show directly is that x is equal to y. So that's what we do. We assume, and we state our assumption, assume x and y are integers and f of x is equal to y. And now we're going to give a little bit of a description of what we're going to do next. We're going to proceed in cases according to if f of x, which we're assuming is f of y, is even or if it's odd. And this makes sense that we'll need two cases. Going back to our definition of the function f, we need to know where things came from, and they came from different places if they were positive or negative, so they led to different outcomes, odd or even integers. So those are the two cases we're going to cover. And the first thing we'll do is consider what happens if f of x is even. So if f of x, which is by assumption f of y, if that's even, then we can write f of x as 2k for some k in the integers, and that's according to the definition of an even number. Now, if we go back and look at the definition of our function, we see that if f of x is equal to 2 times k, then what was put into the function was the thing on the right-hand side of the 2, this value of k. So according to our definition of the function, if f of x is 2k, then x is equal to k. Now, similarly, f of y, which is f of x, is now being written as 2k. And also, by the definition of our function, if f of y is equal to 2k, then y is equal to k. Since x is k and y is k, we now can conclude, by this transitivity of equality, that x is equal to y. So this little paragraph covers the case that f of x is equal to f of y, and they're even numbers. We must now cover the case where f of x, which is equal to f of y, is odd, and that's what we do next. If f of x and f of y are odd, they have the same value, then we can write f of x as 2l plus 1 for some l in the integers, and that's according to the definition of an odd number. This is our definition of what it means to be odd. Now, notice that I've switched from a k to an l. I used a k in the previous paragraph. I would probably be okay to use that k again. The variable k, which was defined in this paragraph, somewhat has local scope. But a lot of people find that a little bit misleading. What variables am I allowed to reuse and what am I not? So I just went ahead and switched it here. Switching is almost never wrong. And reusing is only sometimes okay. So it's better to be safe than sorry. Coming back to this, we're saying, according to the definition of our function, just as before, if f of x is 2 times l plus 1, then x is actually equal to minus l. So for this, you have to maybe go back and look at the definition of the function one more time. Let's see. When we defined our function, we took our natural, remember this is supposed to be an n, we took this number n and plugged it in here, and because it was a negative number, we multiplied it by -2. So if I'm writing an odd number as 2l plus 1, then I'm taking this minus sign and attributing it now to this letter instead. So, staring at the definition of our function, if f of x is 2l plus 1, then the x we plugged in order to get 2l plus 1 must be minus l. Similarly, we can apply this reasoning to f of y. Remember that f of y is equal to f of x, and we've written f of x as 2l plus 1. So f of y is 2l plus 1. And we again look at the definition of our function to conclude that y is equal to -l. Lastly, using this transitivity of equality, x is -l, so is y. X and y must be equal, and we've shown that if f of x and f of y are odd, that x is equal to y. At this point, we've covered all cases. All numbers are either even or odd. We've covered both cases, and in both cases, we came to the same conclusion, that x is equal to y, which is what we needed to do in order to show that this function f was injective, 1-to-1. So at this point in time, the proof is complete.